So I've got a custom snap circuit design of mine to share with you today. You know, about a year ago I put together that custom alarm circuit that kind of just slap things together. This actually, I kind of got the initial design from off the internet. This is the initial circuit design because I was kind of looking around at stuff and found that. And I thought to myself, I wonder if that could be replicated in the SnapCircuits system with its components. And in fact, it can be. It doesn't quite have the same values for some of the components or the same output that's expected, but it still performs a very similar action that original circuit replicates. But I've added additional components and changed values and things like that with my own circuit design here to kind of get my own custom output and actually be able to see the interaction going on in the circuit. Now, again, the SnapCircuits system is designed to be used by young and older people alike. With this circuit, I would really suggest that it be undertaken by someone that's experienced in electronics or an advanced user of the SnapCircuits system, because this circuit is dealing with high voltage DC on its output. And I'm saying this because it's out of safety's sake. You know, I don't want anyone to try to replicate this circuit that I'm showing them and get a nasty surprise out of it. So I'm just pointing that out right now. So the recommendation is, I'm showing it to you, but you don't have to build it yourself. So I'm also going to be showing a gadget that I mentioned in one of my previous videos. We're going to take a look at that right now because we're going to use it to also monitor what's going on in this circuit. And here's the gadget that I was talking about that we're going to use in this video looking at our circuit here. And that's the oscilloscope. And I mentioned this in one of my previous SnapCircuit videos. Now, this is not really going to look at it in depth or anything like it. This is kind of just going to be a small overview because I haven't shown it yet. But it is made by Co. You can see it right there. And it supports a maximum range of 30 megahertz on our frequency that we can read. And it's their S1325, which is a very popular, very common model oscilloscope from Co. And we've got all our different controls here, as you can see, for our voltage divider, our time divider. So time is this way, voltage is this way. So if we got a really fast waveform that we need to look at, something that's really high frequency, of course we advance the time. If it's really low frequency, we want to turn it back. And again, depending on the voltage that we're reading, you know, we can adjust our divider on here if we're reading something that's really low in voltage or really high in voltage. And we can adjust our probe directly on the probe for depending what voltage we're reading. And we've got controls for our CRT and trigger point for our waveform and other things like that. Again, this is just an overview. We're going to look at this a little more in depth in its own separate video. So I just wanted to show that because we're going to be making use of it. So let's go back and look at the circuit, because now I can talk about what's on the circuit and how it functions. So here we are back with the circuit, so I can show you the various components on it and also explain how the circuit operates. We're first starting off with our B6 battery adapter, which we've seen plenty of. It's operating in the 6 volt mode right now, so we're getting 6 volt input on our circuit. We have our slide switch over here, which is going to basically turn our entire circuit on or off. Below that is our NPN transistor, which we know basically acts as kind of an electronic switch. We have our meter connected in series with our green LED. Now, we haven't gotten into the meter yet because this will be introduced in the SC500 project when we do projects 500 and above. And right now, with it connected in series, the meter is acting as an ammeter, so it's measuring current. And we've got it set to the low range, so it's measuring from 1 to 10 milliamps of current going through that loop on the side there. We've got our variable resistor over here, which we already know how that operates. Below that is a 10,000 ohm resistor that's connected to it. And then over here on this side we have 3 components. And we're starting to get into capacitors in our SnapCircuits projects. We haven't really gotten into them yet, especially with how they're configured in series and parallel. We have our C1 and C2 capacitors connected in series here. So that's our 0.02 microfarad and 0.1 microfarad capacitor connected in series. And when you connect capacitors in series, the overall capacitance is actually less. than one of these capacitors by themselves. If we wanted to add them together, we would actually connect them in parallel. So by connecting them in series like this, we actually have less overall capacitance. And we haven't been introduced to this either, because this is also going to be in the SC500 system, is a standard diode. We're familiar with the light emitting diodes, but we haven't worked before with a standard diode. And really the purpose of a regular diode is just one-way current, just like an LED does. Difference is it does not give off any light. So current will go this way, but not that way. And before I really talk about the setup on here, I need to talk about this in the middle of the circuit, which is basically the heart of what makes this whole circuit work. And this is the transformer. And again, this is not introduced yet because it's going to be in the SC500 systems, again with those projects. And what the transformer does, it transforms DC into AC. So we're taking our DC that's coming in from our battery system, and then we're transforming it into AC with the transformer. And a transformer has two sets of windings inside of it. You have one side that has less windings, you have another side that has more windings. And depending on how the transformer is set up, where the input and outputs are on the windings, you can either step up or step down when you transform. In this occasion, we are stepping up. So we are boosting the output with the transformer. And because of that, again, it transforms to AC. But the way the circuit is set up, we will still want DC on the output. And again, that's where our capacitors and diode over here come into play. Because our capacitors, there's a very small capacitance there, so it's not storing a whole lot of charge. And our diode is only allowing the current to go one way on this side. So while everything else works as AC that's on this side of the windings, this side over here still only works with DC coming out of it, because the diode is not allowing the current to go in the other direction. And because of this, with the capacitors, we're actually boosting the voltage on this side. So each cycle is actually boosting the voltage up every time this, alternates. That's why it's called alternating current. And because of that, and this is the main reason why I emphasized at the beginning that this circuit will only be really replicated by someone experienced with electronics or an advanced SnapCircuits user, because our DC output voltage over on this side is over 100 volts at most. So we can get up to 100 volts DC output on this circuit. And the reason I emphasize about that as a safety factor at the beginning is because 100 volts DC you can feel the current with in your body, and you will get a shock. Now, it's not going to really hurt you, but you will certainly feel it if you touch it, and you'll back off. So that's again why I was emphasizing that at the beginning about trying to replicate this circuit, because of that high voltage DC output that we're going to be working with. It allows us to do some neat stuff with this circuit, but again, I wanted to emphasize that because you can be shocked by this. So that's why I say I don't want people trying to replicate the circuit and getting any nasty surprises with it, not paying attention to what they're doing. So let's go ahead and get the circuit powered up and look at our oscilloscope and our meter so I can show you those voltages and the waveform that we're getting out of it. And then we'll start showing the stuff we can do with this circuit. I'm powering on the oscilloscope. I'm also powering on our meter, which is set for the 200 DC volt range. And again, right now we don't really have anything on the oscilloscope that is detecting. And then we turn our circuit on. And there we go, we have a waveform. Now, anyone that's familiar with waveforms in electronics and engineering should immediately recognize this type of waveform. This is a reverse sawtooth waveform. And basically the way the reverse sawtooth waveform here is showing, and this again is working, it's showing from our capacitors. Again, that's our DC output we're looking at. We have a point where we go immediately up, and then the current linearly changes. So there's no curves or anything here that shows any kind of exponential change. It immediately spikes up, and then consistently goes down, and then it spikes back up again, and then consistently goes down, and it spikes up again, consistently goes down. And that is how our sawtooth, reverse sawtooth wave appears on the circuit. Now again, I mentioned that there is a variable resistor on that circuit. That variable resistor is designed to both change the amount of current and the voltage range at the DC output. So right now it's actually at the lowest setting. So let me ramp it up. Now you can see the change. Doesn't show a whole lot of change when we look at it, but the waveform is slightly different. The peaks are a little bit more, and there is just a tiny bit of a curve change in our waveform right here. And I can change my time derivative so we can get a little better look at the waveform there. Again, when we look at it closer, we can kind of see that dip right there. And again, that's at the higher voltage and current output right now. Set this back. And again, we have our meter hooked up too. And that, again, that's our DC output right now. We're getting up to 98 volts at the output. And again, that's on the high side. Low side, change that back. Our low side is about 88.5 volts DC. Go back up to the max. And we get a 98. Now I can coax this circuit if I put my finger somewhere. And see, now I'm pushing above 100 volts DC on the output. We're actually 101.5 that we're getting up to. But see, I was using my hand to provide resistance in a certain spot to coax the circuit into upping the voltage a little more. So again, that's what our waveform at the output looks like. This is what our voltage at the high side looks like right now. Now let's go back to the circuit and let's start playing around with some stuff, and let me show you what this high voltage DC does. Okay, now I've zoomed out all the way because I want to make the circuit visible so you can see our LED and our current meter here. You can see max deflection on the meter right now, plus our LED is lit up. So we got 10 milliamps going through that loop, and we've got our variable resistor all the way over to the side. You probably can't hear it because it's not making enough noise, but there is a high frequency sound that is coming from our NPN transistor because of the transformer passing through it. But again, remember how I said that you can get an electric shock from this? Well, since I'm the one doing this video, and I emphasize safety again because I'm the one doing this, I'm the one that's going to get shocked for you. So I'm going to take one of our output electrodes, put my finger there. I'm going to take my other one, and again, you may not visually see it, but I want you to pay attention to our meter and LED there. So you probably can't see the deflection that much going on there, but I can assure you that I am getting a jolt here. Because I'm getting a sensation in my fingers, both on the black and the red here. Because while my one over here is sitting on it, I can feel the electric pulse go through there every time I tap the red here. Same thing over here, I'm feeling it on the red side when I tap. And I can hold. And again, I can feel the electricity, but also I can feel some heat build up. So I gotta take my hand off. And again, pay attention, I am using this on the low voltage, low current side. I am not using it on the high side. Again, for safety reasons, because I really don't want to shock myself. Now, I'm not showing it. Let me move the camera back over here to the oscilloscope. Again, there's our current waveform. When I get a shock, you can see the waveform change. See, when I hold it, you can see the waveform change. Let me change our voltage divider so you can see it a little better. See, I'm getting zapped. Getting zapped there. See if I can bring that down even more. Okay, you can see that. And you can see that there is some exponential change there on the waveform. Oh, man. I can really feel the shock there. So I'm going to stop. Yeah, after doing that for a while, you start to really feel it after a while. Maybe bring that back. So again, I was getting an electric shock there, and you saw the waveform changing because of the voltage drop that was being incurred there. Now, I wasn't showing the voltage meter here at the same time, but this was going down, indicating that it was encountering resistance. So it was getting a voltage drop. Go back over here. Now, let's see. I'm going to turn this up to high current. Now you can see that our current range here has dropped a little bit because we don't have so much going through there, but our LED is still lit up. Now I'm probably going to have to zoom in on this for you to see it, because I want you to see the electric spark across the electrodes. So I don't know if the camera will focus or if you'll be able to see this. I also got to do this without touching the electrodes myself. Again, I'm operating on high side because I don't know what this would do. Alright. Again, the camera's not focusing well, but you should still be able to see it even when it's unfocused, the little sparks. So you can see the little sparks there. That's the high voltage discharge between them. So that, again, that spark is that 98 volt DC coming into contact with each other and arcing between those two contacts. And again, I couldn't show you because I was zoomed in, but the meter was deflecting over and the LED was getting bright. I can still show that here. Well, actually, the LED goes down. I take that back. It goes the other way when it's over there. See, that goes down because there's current going through this loop now, so there's not enough going through there this time. So that drops. Now again, the same thing this way. If I do that, you don't get as much change. But there's still just enough of a spark. See, you'll still see the spark there. Now another interesting thing I'll show, to prove that I did in fact have current going through me, I am going to light up an LED passing the current through me, and I'm actually going to use another thing that we haven't seen yet. This is our multi-LED display. We haven't quite gotten into that because again, that's also a component in the SC500. Now, I can still light that up, but I'd rather not have to deal with feeling the shock of the current going through, so I am going to put our 100,000 ohm resistor on there. And now I'm going to hold the black over here with my other hand, and then I'm going to touch this. And you can see that I am lighting up the LED portions when I touch them, because I am passing the current from here and completing the circuit. And again, the reason for this is because of that high voltage DC. It's able to pass enough through me that I can light this up. And because I'm using resistor 5, this 100,000 ohm resistor, I don't feel the shock like I would if I didn't have that there or used a lower capacity resistor. So if I use a lower capacity resistor, yes, this will light up brighter, but I will also feel the shock of doing it. And again, with that resistor there, I just can't put enough through my body to light up multiple sections. But it does prove that, yes, I can transfer energy through my body. And here's another fun way that I can also prove that. We have our whistle chip. A whistle chip is a high resistance, low current device. that can produce audio. So I don't need a resistor for this. And I've got that set on the low side right now. So again, I'm holding this over here. You don't hear much audio from there. Let me adjust this. Touched the other part spot by accident. Usually it's supposed to make some more buzzing or something like that. I'm surprised it's not doing it this time. Again, there's still audio coming out of it. So that proves that part. And get one on the high side output. Let's see, 98 volts on the output still right now. Now, here is some of the most interesting parts of it that I want to show you. Alright. This is a standard CFL, compact fluorescent bulb, used on standard 120 volts AC. Obviously everyone should be familiar with these. But I want you to pay attention what this bulb does when I connect it across these terminals. So I will put my positive there, almost like a light bulb socket. Take my other one here. And again, I've got this on the high output, so it's got the max voltage and current that can come out of the circuit right now. Just trying to get this thing set up and get my arm around the camera. Put that there. And I'll bring this terminal over. And as you can see, I'm turning on and lighting up this CFL. Now, there's not really enough current output to overcome the transformer and everything that's inside the CFL to make it constantly glow without flickering. This is kind of typical of a CFL that's just not getting enough current. It may also be the frequency coming out of the transformer, just may not be able to handle it. But we're actually powering up this 120 volt AC CFL with this circuit. And again, it's flickering because it can't really maintain enough current to keep it constantly on. But we were able to ignite it, and ignite the gas, and make it light up. So that's one of the interesting things with the CFL. But here's the best thing so far. This, of course, is a 120 volt AC incandescent bulb. This is 4 watts, used in night lights. Now, watch what happens when I put this across those electrodes. Now, this one fits in a little better. Hold it right there. It glows. It lights up. Now, is that cool or what? I'm trying to keep contacts on here. And again, if you're listening very closely, you might be hearing the whine from the NPN transistor from the transformer going through it, if you listen very closely. Well, we are lighting up this standard 120 volt AC 4 watt light bulb with this circuit. Now let me pause the video for a second and show you how that variable resistor will affect this. Okay, so I used some alligator clips so I wouldn't have to hold it, so that's got it connected on the positive and negative ends. Although with that, it doesn't really matter. But I'm going to turn my circuit back on. You see that our light powers right up. And you can see that we do have a pretty good voltage drop, because we're down to 33 volts DC coming out of there. But if I adjust my variable resistor, see, I can make it a little bit brighter because I can adjust voltage and current slightly with that variable resistor if I slide it back. Let's see what I can do here. Got it up to, let's see, 36.2 volts is as high as I can get that. So yeah, I can only get that up to 36.2 volts. Well, we got the voltage a little bit higher, so the bulb was a little bit brighter. But as you can see, that bulb is being lit up from our DC output of the circuit here. Again, you move this, you should see the bulb change just a little bit. And again, you can certainly see the change in the LED and meter deflections when we look at it adjusting our current. But about the midpoint there is about the brightest that we can get the bulb, where our voltage is the highest we can get it on that output. And again, I need to check my B6 adapter. Yeah, it's getting a little warm on its thermistor. Turn that circuit off. Now again, if I had the variable resistor all the way to the side here, when I tried to light up that CFL, the CFL would never light. There's just not enough current to turn the CFL on with it all the way over here. That's why we got to have it all the way up on that side. Let me try that whistle chip again. The whistle chip is supposed to emanate some interesting sound from that. Let's see if I can get it to come on here. Yeah, you can hear the whistle chip a lot better now. Yeah, the audio I was thinking of was actually when I had the R5 resistor there. But when I put that R4 resistor there, I actually was able to get more voltage out of it. That's why it's sounding different. Let's see. Well, I guess for the sake of things, I might as well shock myself one more time, but this time I'm going to use the red LED to again illustrate that I can conduct the DC voltage through my body and light up this LED. So, grab this part here. And again, I'm going to feel the shock of the current going through me. If you see, we've got our, ouch, yeah, see, LED lights up, but I am feeling the current pulse when I do this. So yes, again, I am completing the circuit with my body. I'm lighting up that LED. And yeah, it's just hurt after a while. Turn that off. But that is how this custom circuit works. And again, I just wanted to share that because again, it's got some interesting things you can do with it. But again, as I said, I want to emphasize safety with this circuit because again, as I've shown you, you do pass current and you do get electric shocks from this. So again, it's really best for experienced or advanced users if they're going to try to replicate this kind of circuit. But hey, might as well show you. And besides, that was 6 volts DC being jumped all the way to almost 100 volts DC. So, just something I saw on the internet that I wanted to try out with SnapCircuits and expand upon it, and this is what I got. So, as I say, a little something interesting I wanted to show.